scientists, researchers, and all enthusiasts of astronomy who have joined us today. We are lucky and very happy to have Professor Udaya Shankar from Raman Research Institute. And without any delay, I will invite Dr. Arvind Kulkarni sir, our founder, member of NASNI, and our guide, mentor. He always keeps us excited to work in NASNI and create new things and start and initiate today's formal session, sir. You are muted, sir. Kulkarni, sir, you are muted. Yes. Yes.
Yes. Now, a very formal introduction to Dr. Udaya Shankar Narayan Rao. I want to say that he is not nothing less than a star himself. The reason only I can qualify saying that he is more of a radio star, which is invisible, but it is very powerful also. Many people should know that in radio radiation, the emission is huge, especially things like quasars and others. That is what I learned in my MSc, taught cosmic rays and others. Quasars are quasi-stellar radio stars, and they are far more powerful than the ordinary stars like the sun we see. Okay. His education is primarily in Karnataka and in Bangalore, and he picked up his doctorate in Bangalore, and he worked at Raman Research Institute for a long time. His interesting thing that I want to tell the youngsters here that even at his age of probably 65 or so, he is very active, even doing research. Most of the people stop doing research. He has not stopped doing research, and he continues to serve in three different locations. He goes to South Africa, to Australia, and to South America to set up the telescopes and other things. He's extremely active with the Gauri Noor radio telescope of the Raman Research Institute, and the one in Australia and the one in Chile also. He is connected. He is connected. He also has intelligence development. He is a very good poet. Also, he writes a lot. And with this introduction, I just want to say that when you are an astronomer, you are far more than just doing your routine work. That is the reason, and he takes interest in development of youngsters as well. He was kind enough to address students on quantum learning in one of the sessions here in Bangalore, and he converted into a beautiful session on quantum in astronomy. And then he developed it further on, and he has become progressively useful for us, for quantum, for AI, and also for astronomy. I just thought about introducing him to NASNI because by missing him, NASNI will lose rather than whatever he gains. And as I wanted youngsters here to know more about astronomy, the work of astronomy, the challenges of astronomy that he meets and he works. He will describe everything in detail to us. I don't want to stand between you and him, but it's my great pleasure to bring in Professor Udaya Shankar here. And with that, I end my talk. Thank you very much. Yeah.
So I formally invite Professor Udaya Shankar ji to start your session.
Yeah,
Please.
we'll have to share the screen. So let me just see.
You can share, sir.
Share. Okay, wonderful. I could see share. Right, it's here.
Yes, it is visible, sir.
Yeah, no, it's
Next
visible,
slide.
but I have to make it full screen. So I'm just trying to see how do I get into that mode. Yeah. Is that fine? Now, can you hear me? And can you also see what has been projected?
Yes, yes, sir.
Yes,
Everything
sir.
fine.
Yes, sir. Everything is clear. Thank you.
Very good. First of all, many times the slides don't work when we press go. So I'm trying to see stop share. No, it's I don't know why the slide is not moving.
So you need to share the full screen. The
Yeah, I have already
entire.
done it, ma'am. You are not able to see it. First of all,
It is visible, sir.
it
Sir,
is.
the first screen is visible to us. Try to shift it to the second screen. Maybe it will be visible.
See, first of all, what I find that when in this mode, my PPT is not even advancing. So I'm a bit worried about that. Let me just see. PowerPoint, I don't know what to do.
Hemant sir, if sir could pass on the PPT to you and you could shift the slides.
Yeah, 1 second. Let me try it for the last time. Normally, I haven't had any problem all along so far.
Sir, you can do the entire screen. You can share your entire screen.
Yeah, that is what I have done. I don't know. See, in the Zoom, okay, let me just make
You
it.
try once again, sir.
Okay. Connect a calendar. No, I don't want that. Is this fine now? Let me just see. Let me just say share. Okay. Microsoft PowerPoint, Udaya Point, application Windows. Can you see now?
Yes, sir.
Okay.
You may change the slide once again.
Yeah, now it changed.
Yes,
Yeah,
yes,
wonderful.
yes.
Right. So can I start and take on? Thank you very much. Sorry for the trouble and
Sure, sir. Sure, sir. Please.
yeah. Well, first of all, thank you for your invitation, particularly to Hemant Kumar for having taken the initiative to invite me, and Kulkarni sir for having introduced me to Nasni, and for your wonderful and very affectionate, I should say, introduction. I don't know whether I deserve that. Let us see in the next whatever minutes possible, as long or as short as I can. I will try to convey to you what I want to say. Well, as you know, the focus of my today's talk is cosmology. Since there could be very many of you who are not accustomed to have heard and known about cosmology, let me say a few sentences about cosmology. Cosmology is the scientific study of the origin, evolution, structure, and ultimate fate of the universe as a whole. It seeks to answer questions such as how did this universe begin? How has it evolved over cosmic time? What is the universe made up of? And how it may end? Well, you may also know, or I'm just going to share with you, that cosmology is based on three important parameters: observations, physical laws, and inference and modeling. Observations of what? Observations of galaxies, which are considered the basic building block of the entire universe. The cosmic microwave background, which is known to be a very important relic from the Big Bang, and the large scale structure which tells us about how these galaxies are arranged in this universe. We base our conclusions using the physical laws which hold good everywhere: relativity, thermodynamics, and quantum physics. And the most important thing to understand is the inference is mostly based on modeling and whether the observations fit our models at what level, and we draw an inference from it. So, unlike the laboratory sciences, cosmology studies a single universe. You can't set up an experiment, it's a single universe, and you have to reconstruct its history from the clues which are visible today. That's why I have called my talk as Echoes of Creation. Even though there is nothing which is sort of echoing or throwing back the sound or any electromagnetic waves, it is called Echoes of Creation because you hear about it from all directions. In essence, I just want to share with you that it is a humanity's same attempt to understand the universe by reading its present state as a record of its past. That's a beautiful time machine. The entire astronomy is time machine. When you see a star which is 4 light years away from you, you are seeing what its condition was 4 light years back. So it's a time machine which is taking you back. This concept of understanding the universe is not new but is very ancient. That's why I just have used the title Chasing Echoes of Creation from Ancient Questions to the Square Kilometer Array. What is the Square Kilometer Array? Square Kilometer Array is the world's largest radio telescope project which enables astronomers to observe the universe at radio wavelengths with sensitivity hitherto not known or not thought about. Let us get into it more details as we go along, but let us now just understand that the topic is Chasing Echoes of Creation, Ancient Questions to Square Kilometer Array. Well, combining ancient aspirations and modern cosmology in one talk, I thought would be powerful for teachers because IAPT is Indian Association of Physics Teachers, because it reveals the same human drive, wonder combined with humility, which is common to ancient traditions and also the present day physics. That's why I thought this combination is special. Many ancient thoughts and modern cosmology both start with amazement and wonder. Oh my God, there is a universe at all. And does it show order? Can I see order in the chaos that I observe? These are beautiful, wonderful questions that people in the ancient days have asked, and even today the cosmologists ask. And very important point I want to emphasize, that's why I have taken some ancient thought processes, because you're all teachers, that good science today explicitly recognizes limits of our own understanding, just as some ancient texts have admitted very clearly that, look, ultimately the origins of universe may not be knowable at all. It may remain unknowable for a long time. For example, you might have already heard, even before I talk, my talk, that dark matter, dark energy, quantum gravity are still not very clearly known facts to any astronomer or to any physicist. There are many questions unsolved in all these aspects. So that's why I thought combining ancient aspirations and modern cosmology may have some bearing on the teachers. See, when I put ancient thoughts and modern physics side by side, I don't want you to think science proves scriptures. Oh my God, I knew everything. The scriptures in India tell us everything. No, that is not what I want to state. I want to emphasize that methods have indeed changed. When the ancient thoughts were given in poetic intuition, today we have cosmology which works on mathematical models and data acquired through observations. It is cosmic wonder and intellectual humility which are ancient and necessary for a honest science even today, and that's what I want to share with you or tell you. Humans have always looked up and asked the same big questions. Inculcating questioning spirit is essential to teachers and students. What I want to say is, today in the classrooms, when students ask questions, we don't like it. Whereas at the Raman Research Institute, what I have learned is, please say no when I don't know. Please ask a question which you don't know and try to understand what is it that we are talking about or we are working on. I just want to inculcate the same philosophy in the teachers and the students listening today. And that's why I have taken up this path of ancient thoughts and the modern cosmology. Questioning is indeed the foundation of modern science as much as that of the ancient thought processes. Look at the questions. Ancient, but at the same time not too ancient. Even in the middle of 18th century, we did not know, is Earth the center of universe or the sun at the center of the universe? We thought at that time the entire solar system itself is the universe. And we always had this problem. Is it heliocentric universe or a geocentric universe? We all know that the concept of geocentric universe ruled from 300 BC to 1500 BC. Whereas with the Copernicus, Galileo, Kepler, and Newton, we accepted the heliocentric universe, which sort of ruled in its own fashion from 1540s to about early 1900s. When people understood that stars are away from the solar system, the next question they asked was, how far away are these stars? And they did measure the distance to the stars. We found that the solar system is only about 100 AU, whereas the nearest star is 270,000 AU, showing that even the gap to the nearest star is 1,000 times larger than our own solar system. It's very important because we are moving towards a solar system to a universe, and therefore emphasizing this increased size and the imagination of the people taking us from 100 AU to 270,000 AU is very important. The next question is, hey, we see stars. What are these stars made up of? You may wonder if I share with you that as recently as 1835, I mean 200 years back, a French philosopher, Auguste Comte, stated that humanity will never be able to determine the chemical composition of stars. Well, even if you hear in your course of your own teaching physics to students, don't be discouraged. It is, you all know, whatever French philosopher said in 1835 has been proved wrong. Spectroscopy revealed that hydrogen is the most abundant element in the stars, and stars are made up of Earth-like elements. And spectroscopy, the physics, is the cornerstone of such important understanding. Then the question arose, hey, we are talking about stars which we call the Milky Way. Where is the sun in our galaxy? You may know it was not clear till the middle of previous century, that is around 1930s and 40s, that the sun lies about 26,000 light years from the galactic center or the center of our Milky Way. But the Milky Way itself is 100,000 light years in diameter. So, what we are trying to say is the solar system is in a very remarkably not an important location at all, even in our own galaxy. How hitting it must have been the ego of the human beings to think that we thought we are the center, and then the heliocentric universe, and now we have a galaxy, and the solar system is not even at the center of this galaxy, but we are in one corner. That's very beautiful to appreciate that. The next question arose, hey, is this only one galaxy? Or there are many galaxies? And people soon figured out that Milky Way is not unique in the entire universe. And we live in a universe of 10 to the power of 11 galaxies. Look at this picture. Oh my God. We are surrounded by galaxies. And today we remember, or we know, that galaxies are the building blocks of the universe. It's not the stars. It is the galaxies which are the building blocks. Stars make up a galaxy and their internal parts to it. When once we understood that there is this universe with so many galaxies, the next question that came along is, did the universe have a beginning at all? Well, the answer to this question came from Edwin Hubble's observations, who showed that the universe is expanding and most distant galaxies are moving away from us, and they move faster than the galaxies which are closer to us. This concept of an expanding universe led to the theory of the fact that the universe indeed had a beginning, and that beginning is what we call as the Big Bang universe. It's a very simple way to understand that the expansion of universe could be thought of as a blowing of a balloon with several points marked on it, and these points are nothing but galaxies. As you blow the balloon expands, the galaxies move far away from each other. So, as the universe expands, the distance between galaxies increases, but not their individual sizes. That's what the Hubble showed. From the concept of Hubble's expanding universe, there were many logical steps. One was that an expanding universe today implies a smaller, a denser, and a hotter universe in the past. Very important to appreciate this. And then the Hubble's observations ended a static cosmos. Hubble's result ruled out a permanently static universe and forced the entire cosmology community to rethink of the cosmic history, in those days, of course. And that is what gave to the birth of a Big Bang idea. Imagine a very simple thought experiment. We are playing a video. It's composed of a large number of galaxies. And in that video, the nearby galaxies are moving slowly, the farther ones are moving very fast. Make a video like that. I mean, don't ask me how to make a video right now. I mean, imagine that it's a thought experiment. And then, when once the video is made, you just rewind it. The rewind takes you to an earlier epoch, and now, after a while in the video, the galaxies move towards each other and they coalesce. And this is the beginning of the entire universe. We model it as the beginning of the universe, and it began with a Big Bang. If that's the answer that we can arrive at by looking at playing at a video and a thought experiment, the next question arises, how old is the universe? How old is the universe can be understood by knowing how fast the universe expands. Hubble measured how fast these galaxies are moving away from us, but it was orders of magnitude larger than what we know today. Today, an accepted value of the Hubble constant, the rate of expansion of the universe, is 70 kilometers per second per megaparsec. What does it mean? Parsec is 3.2 light years, mega is million. So, when you take a galaxy at a distance of about 3.2 million light years, it is moving away from us with a speed of 70 kilometers per second. That is what the Hubble constant says. So I repeat, Hubble constant says that a galaxy which is 3.2 million light years away from us is moving at a speed of about 70 kilometers. By this, one can deduce the age.
నాన్న ఏం కనిపిస్తుందా? రౌండ్లో తిరిగేస్తుందా? ఏయ్,
ionization potential or the temperature of the hydrogen atom, then you start the electron and protons combining together to form hydrogen and helium atoms. So that's what that was happened in the very early universe. This is what we call as primordial recombination. The oldest light arising from the universe, which came after 380,000 years of the Big Bang, is the very important light, which is what we call as the relic of the Big Bang. And that was detected by Penzias and Wilson, and they were awarded Nobel Prize in 1978 for this. That is known as the cosmic microwave background. This was the light that was emitted by the universe 380,000 years after its birth. Then we have the CMB, but still it was a dark age. This is the period between the time when the cosmic microwave background was emitted and the time when the evolution of the structure of the universe, led by the gravitational collapse of objects, in which the first luminous objects, or we can call them as stars for the time being, were formed. So there was a dark age. And then there should be light, and there were gravitational collapse happened, and bright led to formation of stars, and these stars emitted very bright radiation which led to reionization. So we have a fairly good understanding saying, or a good model saying that we have a universe which was very hot. As it expanded, it cooled. The cooling led to primordial recombination, but still, this is the primordial recombination stage. After that, we had the cosmic microwave background emitted. After that, we had a dark age. Then the stars were born, the cosmic dawn, and then there was epoch of reionization. That is, the neutral medium became once again ionized. So this is the model of the universe as we understand it today. But has anyone seen the first stars born in the universe? Well, let me tell you, the answer to that question is no. No one has seen the first stars which were born in the cosmic dawn. And that is a very challenging topic, and let us look at it a little bit. Well, at this time, as I told you, I want to share with you a little bit of ancient science, or it's not ancient science, it's ancient thinking. There is a very famous Nasadiya Sukta, which is humanity's oldest recorded cosmogonic hymn. It was composed 3,000 years ago, which describes the state of cosmic, that is the universe, non-existence before creation. Look, in 1800s, we were still thinking about heliocentric or geocentric, but here was a Rishi who wrote Nasadiya Sukta 3,000 years back and talked about what does it look like. So the word Nasadiya comes from na, not, asat, non-existence, or which is not, that which concerns with non-existence. So Nasadiya Sukta tells us about the non-existence. Neither there was sky, nor there was anything to look at, is what the Nasadiya Sukta says. To me, I am sharing this with you not to say that our scriptures knew everything, but to show to you that the Indian thinkers, as we are, were capable of independent thinking even so much time in back. And today, as teachers, I want to encourage questioning and independent thinking. So I just want to, all of you, to just close your eyes, and I'll just play a YouTube video of 2 minutes to make you hear this sukta. Let me just try to synchronize so that you can hear this very correctly. Just give me a minute. Can you all see the video?
No, sir, only link is visible.
The link is visible, or should I share? I mean, skip. Can you see now?
You'll have to present your screen again.
Should I share the screen again?
Yes, sir.
I think so. Okay, fine. Share. But it is not giving me the share. Oh, no, this is a different share. I'm sorry. I should go to the Zoom and then share. Thank you. One second. One second. No, this is not the Zoom that I want to share. Where is the Zoom that I want to share? Uh-oh. I don't know why today the Zoom is taking me away to a calendar rather than to the Zoom itself. A bit. I'm in the Zoom, but Zoom Workplace. No, I don't know. Meetings. I'm in Team Chat. What are you seeing right now, sir? You're still seeing my screen?
No, sir, we are seeing the link of YouTube.
So
Oh,
the
you're seeing the link of
presentation.
YouTube? Oh, I see. Okay. But
Yes.
you're not able to see.
Now,
Then if it's just that the YouTube is not playing, is that what you're saying?
yes,
Now it's
now
seen,
it
sir.
is
Now
visible.
it's seen.
It's
Now the
seen. Okay,
YouTube.
fine. So can I play the video for one second? If you give me, I'll play the video.
Yes, sir,
Give
yes,
me.
sir.
Yeah. Just close your eyes and then just listen to it. Can you hear now?
Yes, sir. Audible, sir.
Can you?
Yes, sir.
न मृत्युरमृतं तर्हिण रात्र्या अग्नासीत् प्रकेतः आनीतवातग्स्वधया तदेकम् तस्मात् तान्यदपरः किञ्चनासा तमआसीत् तमसा गूढमग्रे प्रखेतम् सलिलपुं सर्वमा इदं तुच्छेनाभभिहितं यदासीत् तमसस्तन्महिना जायतैकम् कामस्तदग्रे समवर्तताधि मनसो प्रथमं यदासीत् ततो बन्धुमसति निरविन्दन् हृदि प्रदेश्या कवयो मनीषा तिरश्चेनो विततो रश्मिरेषा अधस्विदासी दुपरिस्विदासी प्रेतोधा आसन् महिमान आसन् स्वधा अवस्था प्रयति परस्ता को अद्धा यं विसृष्टि अर्वा देवा अस्य विसर्जनाय अथा कोपेदयत बभूव इयं विसृष्टिर्यत बभूव यदेवा दधे यदेवान यो अस्याध्यक्ष परमे व्योमन् सो अङ्गवेद यदेवान वेद ओ शा तिष्ठा तिष्ठा
Yeah, now can you see my slides again back,
Yes,
please?
sir. Yes, sir.
Hello?
Yes, sir. It is visible.
Yes, sir, we can see the slides.
Once again, my volume has decreased. Can you see my and listen to me now?
Yes,
Yeah.
sir.
Yeah, thank you. Thank you very much. I don't know how well it played out. Don't worry. If you have just looked at this, you can go back home and play it for yourself. And there is very beautiful description of everything in that, in a sense of the word, what you call as the English meaning of that is very clearly given. So there won't be any problem for you. Look at that. The a hive that was constructed 3,000 years back, it talks about there was neither the realm of space nor the sky beyond it. How did this man 3,000 years before thought of that? There was no sign of night or day. That one, the universe, breathed without breath by its own power. Apart from it, there was nothing else. Darkness there was in the beginning, and all this was hidden in the darkness. You saw that the present model of cosmology is very close to this. Everything arose through the power of heat. But, one second. But who truly knows? Who can say from where all this came and how creation arose? The gods themselves came later than this creation. Look at that once again. The courage that this gentleman had when he wrote this. Gods themselves came later than this creation. From where this creation came into being, whether it was formed or unformed, the one who watches over it, the highest heaven, perhaps knows. Perhaps he does not even know. The most important aspect of physics is uncertainty. It's not uncertainty of quantum mechanics, but to understand that the experiment that we do and the inference we reach could be uncertain. And if everyone pays attention to such details, the science will grow better. It is to say that kind of a thing that I played this video for you. Once again, it has stopped. Let me just share it again. Chat, react, video. Can you all hear me again, right? Still no problem? Okay. Fine. Now I think let me just share once more. Presenter layout. Can you see this, please?
We can see, sir.
Yeah, wonderful. Thank you. Sorry for that. Okay. All that I wanted to say is new leaves and old roots are what makes tree magnificent. New knowledge and old principles mold themselves to become dharma. Wisdom of sages can blend with new sciences. It would benefit the humanity. That's what one of the very famous poets in Canada called D.V. Gundappa, who is named as D.V. Gundappa, whose name is D.V. Gundappa, wrote this. And it's very important for all of us to appreciate this. I am not trying to say that modern cosmology has proved everything that was said, but I want to encourage you to encourage your students to ask questions, to think independently, and to wonder about science, and that's what it's all about. You see that Nasadiya Sutta had all this concept in it. A hot plasma, its expansion, primordial recombination. No, it's not mentioned. Dark age, the cosmic dawn. All these aspects were there in his thought process, and that is unbelievable and excellent. But then if you come to modern cosmology from there and ask the question, hey, you talked about a 13.7 billion years universe, how much of this space is still undiscovered? The point is 96% of this universe is still undiscovered. NASA says the universe is 13.7 billion years, but if you look at this slide, the normal matter which we all understand is only 4%. The universe consists of 73% of dark energy and 23% of dark matter, and we don't know what it is. This is where the modern cosmology came in, not just before we understood the constituents of the universe, but during the phase when cosmology was looking, oh my God, what should we do? What changed the entire concept of cosmology was that the stars, the celestial objects, emit not only visible light, they emit all along the electromagnetic spectrum. And astronomers soon found out that we don't have only optical astronomy, we can have radio astronomy, UV astronomy, infrared astronomy, X-ray astronomy, and gamma ray astronomy. Together with all these astronomies, transform the cosmology into a multi-wavelength science, showing that every wavelength tells a different part of the same cosmic story. And you will find that the universe, as observed, mostly the galaxy, as you see here, from radio to gamma, they don't look alike. They look so different from each other. Therefore, you will find that a 15 orders of magnitude in wavelength brought out from the hiding the celestial sources into view, whether it was supernovae, active galactic nuclei, pulsar, transient events, all of it were thrown out open for astronomers to study. Yet, cosmology's deepest secrets remain inaccessible. Even today, it remains inaccessible. So, we had visible optical astronomy, the astronomy became multi wavelength, but still, not all the secrets of the astronomy, the universe has been understood. It is there the radio astronomy was a very important role to play even today, even though it came into existence in the middle of the last century. Radio astronomy observes in the wavelengths ranging from 1 millimeter to 10 meters, that is from 30 gigahertz to 30 megahertz, and the spans sub-millimeter and millimeter bands through the centimeter waves to meter waves. A very large range of wavelengths the radio astronomy caters to. It observes celestial sources, as Kulkarni sir said, very bright. It looks at synchrotron radiation. It looks at synchrotron radiation, which are relativistic electrons spiraling in magnetic fields in seven different kinds of radio sources. It looks at maser emission, like laser. You have maser emission in sources. My God, the 21 centimeter hydrogen line emission is most abundant in the universe. What is this? This is nothing but a neutral hydrogen atom in its ground state, has a hyperfine structure. Depending on whether the spins of electron and proton are aligned or non-aligned, the emission or absorption of a 1.4 gigahertz takes place. Very close to the mobile radio communication, 1.4 gigahertz or 21 centimeter hydrogen. This plays a very important role in understanding cosmology. So, all these things make radio astronomy unique in probing very important aspects of the universe. Let's just skip a couple of slides and look at this. Look at this. If you are looking at optical astronomy, this is what you will see, the stellar light distribution. Whereas if you look at 21 centimeter, this is how the picture looks like. So different from this. So the radio astronomy started telling you many more details of celestial sources that it observed. Radio telescope shows things which are hidden at optical wavelengths. Look at that. Not seen. What? You look at radio, you see all these things. That's why this is one of the largest radio telescopes, which is a single dish telescope, which is 100 meters wide diameter in Green Bank in US. It operates at 3-meter wavelengths and has a resolution of 1.8 arcminutes. Well, this is a problem. What is the problem? The eye has a resolution in visible which is of the order of 1 arcminute, whereas a 100-meter telescope working at 3-meter wavelength can only give you 1.8 arcminutes resolution. This was the problem the radio astronomers faced in the early days. The radio waves are meter long compared to micron long optical waves, and therefore they had to build very large telescopes to achieve the kind of resolution they were looking at. But even a 100-meter telescope, which is single dish, has a fantastic sensitivity. With this Green Bank telescope, in the frequency range of 21 centimeter, 1.4 gigahertz, it can see 0.1 to 0.5 millijansky. What is this millijansky? Jansky is the man who discovered or who first saw radio waves coming from the outer space, and that's why the sensitivity is measured in terms of units of Jansky. The flux density is given his name Jansky, and we can see millijansky. What is this millijansky? I don't understand, sir, you may say. Don't worry, I'll tell you. If you take a 10-meter dish, collect radiation coming from it over a bandwidth of 100 megahertz from a one Jansky source, it delivers only 7.85 into 10 to the power of minus 17 watts. Very, very faint. And this much of radiation would take 1.7 billion years to heat 1 milliliter of water by a single degree Kelvin. My God. So little is the amount of radiation that we collect from the radio objects in the sky, and we need extremely sensitive equipment. Look at what the radio astronomers did. So they built a VLA, a very large array, which consists of 27 25-meter antennas spread over 36 kilometers. What did it do? It acted as though this 36-kilometer is a single dish and gave images which are only, for example, at 45 gigahertz, it has a synthesized beamwidth of 0.043 arc seconds. That means in radio, by building a radio telescope, an array of telescopes with 36-kilometer baseline, radio astronomers were able to beat the resolution of the eyes. And now the highest resolutions are achieved in radio by arrays which were spread across continents. But let's not worry about that for the time being. Let us look at arrays which are in one place. Like, for example, VLA is a 36-kilometer baseline. Similarly, we have in our own country a radio telescope called Giant Meter Wave Radio Telescope. Professor Govind Swarup is recognized as the founder, and Professor Govind Swarup is recognized as the founder and pioneer of Indian radio astronomy, and it was he who built this radio telescope. Is no more, but I just want to emphasize, look at that. He's a BSc in physics from Allahabad, MSc in physics at Allahabad, went on to do PhD in electrical engineering, physics and engineering. And then he is the one, the pioneer, who built, even today, one of the world's largest radio telescope in India. What is it called? Suddenly, sometimes it doesn't like, okay, maybe it doesn't like this because of this, I'm out of this thing. So what did he build? He built a very low-cost 45-meter dish. He used a very special concept of a stretched mesh attached to rope presses. He used to call it this as Indian rope trick, jocularly. And he built a 45-meter dish, one of the largest dishes in any array that you find in the world today. And it's all made in India, built by an Indian astronomer. That's what I want to convey to you, teachers and students. And look at that. He had 30 dishes, 45-meter in diameter, spread over approximately 28 kilometers. And what did this telescope do? My God, at 1.4 gigahertz, it can achieve a resolution of about 2.3 arc seconds, and it can see a source in the sky which is 2.5 microjansky. We had millijansky for a 100-meter telescope. Now we are talking about baselines which are 30 kilometers, 30 45-meter dishes going to microjansky's level. My God, what a change in sensitivity. But alas, even then, have you seen anything? I started my talk saying, cosmic dawn, the first luminous stars were born. Have you seen these stars? The answer is no. What you mean by that is the existing data sets include an image of the universe when it was 0.4 million years old, as well as images of galaxies when the universe was older than a billion years. So between 0.4 million years to a billion year, we don't have any observations carried out. There are some galaxies which newly, constructed JWST, James Well Max Telescope is showing, Hubble Telescope has shown a couple of galaxies, but it's far, far away from what we want to know about the early universe. So I repeat that even though we have reached micro-Jansky level of sensitivity, the existing data sets do not have images of objects between zero point 0.4 million years to approximately older than a billion years, between 1 billion years. And that's why we wanted a square kilometer array. So, a square kilometer array was a concept which was started by Govind Swarup and many of his colleagues at the time, way back in 1998, and it has taken 25 years to come to a position in which we have started building it, and we may see the end at the light of the tunnel. The Square Kilometer Array is the most ambitious radio astronomy project ever attempted. It has 10 to the power of 6 square meter collecting area, 1 kilometer by 1 kilometer. It's not 1 kilometer by 1 kilometer, but it has an effective collecting area of such a large dish. And it has a very high resolution because the antennas could be spread up to 3,000 kilometers. It has a very wide frequency range from 70 megahertz to 10 gigahertz. It is located in Australia and South Africa, and they are located in very radio quiet regions. I will show you, far away from any human habitat. And I just want to tell you, it costs of 1.5 billion euros. It's $1 billion project, very huge. You look at that. When radio astronomy began in 1950, if you look at the sensitivity as 1 unit, today we are talking about sensitivity which is million times better in about 75 years. 1950 to 2025, we have a million times sensitive radio telescopes. And what is SKA? SKA will be 50 times better than any of the telescopes that we have in the world today. And that's what we are trying to do and what we are trying to achieve. I'll just quote a very nice poem by Mary Oliver, who says, "Tell me, what else should I have done? Doesn't everything die at last and too soon? Tell me, what is it you plan to do with your one wild and precious life?" Astronomers answered, "I want to build the world's largest radio telescope." And that's what the astronomers are doing. One telescope with 2 sites in Australia and South Africa and its headquarters in Manchester. And that's what we are building. Creating the world's most sensitive radio telescope, 50 times more powerful than anything built before. And that is really amazing. And where have we gone? Because if you are looking at such whispers from the universe, you have to go to a place where the man-made interference is very low. So we have gone to remote deserts in both Australia and South Africa, where the human population is 1 in 100 square kilometers. That means you have a 10 kilometer by 10 kilometer, you will find only one person. And that is Western Australia desert. Similarly, it is so in South African desert. Can one country build such a huge telescope? No. It is a global collaboration with Australia, Canada, China, South Africa. My God, you name, except United States of America themselves are not there. You accept that, it's a huge multinational collaboration. The South Africa consists of dishes. It consists of 197, 200 dishes approximately, each of about 13.5 to 15 meter diameters. And its maximum distance is 150 kilometers. Look at that. The baseline in GMRT is 30 kilometers. This is 5 times larger in diameter. And that's the kind of equivalent diameter, or the longest baseline, as we call it as. The SKA in South Africa, SKA low in Australia will have 130,000 antennas. 130,000. It will operate in the frequency range 50 to 300. And the distance would be, the longest baseline would be of the order of 74 kilometers. My God. such a large telescope cannot be made in one go, and therefore the construction strategy is to go in several stages, and they expect by 2028 June or 2029 or latest by 2030 the entire telescope will be operational, but by 2026-27 there will be some data that will be released soon, and that's the construction strategy that we are planning. So, what are we talking about? We are talking about 1.3 billion euros to make 130,000 antennas, and that will give you data, both combined, approximately 700 petabytes per year. Huge amount of data. And look at that. There will be regional centers to process this data and to disseminate the information from astronomy to people, to scientists, to teachers, and to students who are interested. And look at that. If you compare it to the Facebook, today the data of the Facebook is the order of 180 petabytes, whereas SKA will be 300 petabytes. What a large data center SKA will produce. And name any science, cosmology, how did the life begin? The early universe, continuum sources which are very far away, gravitational waves, any kind of astronomy related physics that you want to study, this sensitive telescope can do for it. It is built in the lands of aborigines of Australia and also in South Africa. And here they are wishing us all the best to make the telescope workable. But very surprising, I visited both the sites, I was very lucky. And we think that deserts have nothing, but look at this. Deserts are a home to a variety of plants and animals. Amazing display of flowers and colors. And this is a very beautiful medium-sized lizard in Australia, Western Australia. And these are the pictures of the telescope. Because I'm taking longer time, I just want to close it down. So I'll just very hurriedly show you these pictures. Look at that. This is a cluster of antennas in the center, which is from SKA low telescope. When 4 stations were installed in August 2024, but we still have a long way to go. But look at that, SKA mid telescope is getting installed, and this is where I was, for example, in this picture. If you look for me somewhere here, yes, I'm here, wearing lots of warm clothing, and that was very recently in 2025 September, where I was in South Africa visiting all these sites with the other scientists in the world. I was representing India in this team. And so we have SKA low, which will have a resolution of 0.5 to 2 arcseconds at low frequencies, which will have a sensitivity of 1 to 5 microjanskis within 1 hour, and it will see the cosmic dawn. It will see reionization of the universe. It will see large amount of transient detection. SKA mid will have 0.1 to 1 arcsecond across a large frequency range, and you can study galaxy evolution, active galactic nuclei, radio bursts, and the combined SKA between SKA low and SKA mid will be able to map 10 billion galaxies and can give you a wonderful universe's full history. Unprecedented sensitivity, effectively seeing everything from dark ages to cosmic dawn. So, in Indian government, taking into account that this is a very important project, has approved 1,250 crores as India's contribution to this world's project. And by this, the scientists, teachers, and students will have priority access to the best radio observatory in future. And therefore, there will be lots of institutions which are working, and you will have an opportunity to collaborate with them. And there will be lots of social benefits. Interest in science and technology in general will increase. Hopefully, people like me will go and talk about it to several students and teachers like you and enhance India's standing in both politically and scientifically in several this ones. So, a word of advice for you is be prepared for everything. Let your karma arise and dance. Let the divine one sleep. Miracles are not impossible. There is no limit for magnificence, and get ready for everything. The future of radio astronomy lays in the hands of young engineers and physicists that you teachers can build or can motivate in future. and it should be driven by curiosity and innovation, not just copying only what is available around. But remember, we had a very ancient tradition and a modern cosmology, both in this country. And I want the youngsters like you listening to this talk to play a very prominent role in developing radio astronomy of the future. So, what is the present status? We are running to get the lift required for a quantum jump in radio astronomy. And thank you very much for listening to me for so long with a lot of patience. Thank you.
Thank you so much, Dr. Uday Shankar Naranji, for such a elaborated and thought-provoking talk. And it was a uh, good chance for us for starting 2026 for listening you for all lengths and breadths regarding the radio wave astronomy, and you have shown all facilities, global facilities for this kind of astronomy to us through your talk. Now the we invite the questions from our
I
audience.
hope I have not put all of you to sleep. And yeah, fine. Can you see me and now listen, hear me?
Yes, sir, we can see.
Wonderful.
Now
Yes,
we
please
invite
go ahead.
questions from
If
our
there are any
audience.
questions, if I know, I will answer them. If there is something that I do not know, we can always go back and learn again. Yes, madam, tell me.
Yes.
Sir, I would like to start with asking the questions. Uh, Actually, your talk was extremely informative, but for people like me who are not from a physics background, uh, the things were pretty technical.
Yeah,
Frankly
sure. Thank
taken,
you.
they were
Thank you for
really
saying that.
technical.
Yes. Because it was meant for Indian Association for Physics Teachers. I made it for physics teachers.
I understand, sir. But yes, we understood a part of radio astronomy, what radio astronomy does and how does it work actually. Because getting the radio waves from the heavens is really a difficult task, which I have understood it very well. But
Beautiful.
yes, I have heard that people are doing radio astronomy from their home itself. Is it possible to do that? A project called as RAD at Home is run.
Correct.
How,
Correct.
how do we do that?
Beautiful. You should send this question to Anand Hota. He will be very happy to explain it to you. But I can tell you what he does. See, what he does means how it's very interesting and very important for people like you who are not experts to get involved in that. That's what I told in the last slide that I showed. That the if square kilometer array reaches you, it is wonderful. So what Anand Hota is doing is he is taking several projects, particularly the project of SETI, Search for Extraterrestrial Intelligence. The data is available. Your laptop, when it is free, is being used for analyzing data, and you also take a part in that data. Some part of the data will also come to you. You also analyze it and send it back, and therefore you do astronomy. You see, I told you that modern cosmology, if you listen to my first slide, I said, is dependent upon models and observations. Not all of us can observe going to a radio telescope. So they collect the data and give it to you. And you use the models and analyze the data and then ask yourself questions in physics and science which will excite you. That's what astronomy at home is, in my simplest way in which I have explained. And Anand Hota has done a great job bringing so many